All right, so today we're going to be talking about section 8.1, which I know is a little weird, but remember we started the chapter with 8.2, then we went to 8.3, now we're going to go back to 8.1. The reason is because 8.1 is kind of a hodgepodge of all sorts of different kinds of sequences and series. And it can seem a little overwhelming when you're given all sorts of variety of things. So what we decided to do was start with 8.2, which was just arithmetic, which was nice because we have formulas. We moved to 8.3, which was just geometric. Again, nice because we have formulas. But now we're going to go back to 8.1, which is more generalized and doesn't always have nice formulas. And it's kind of a hodgepodge of things in this section, but at least you've seen some stuff with sequences and series already, and so that will hopefully make this section a little bit easier than it has been in the past for our students. All right, so first thing I want to kind of touch base on is an explicit sequence. You've been dealing with explicit sequences already. That just means that whatever term you want to find, that's the number you plug in. So if I want to find the first three terms, like let's say I want to find the first term, then I'm going to just plug in a 1. So a sub 1 would equal negative 1 to the first over 2 times 1 minus 1. Well, negative 1 to the first power is a negative 1. And then down here we would have 2 minus 1, which is a 1. So our first term ends up being a negative 1. If I want the second term, I'm going to plug in a 2. So a sub 2 would equal negative 1 squared over 2 times 2 minus 1. So again, if I want my second term, I'm plugging in a 2 in for n here and here. All right, well, negative 1 squared is a positive 1. And then down in the denominator, we'll have a 3. So my second term is a 1/3. To get my third term, I'm going to plug in a 3. So a sub 3 will equal negative 1 to the third over 2 times 3 minus 1. Negative 1 to the third is negative 1, and then we'll have a 5 in the denominator. So our third term is negative 1/5. One thing I just want to point out, do you notice how the first, like if I write this list of numbers, I would have negative 1, comma 1/3, comma negative 1/5, etc. When you notice alternating negative, positive, negative, alternating signs, likely it is because you have a negative number raised to a power. So when that power is even, a negative number to an even power is positive. But when this power is odd, a negative number to an odd power is negative. So that's the reason for the alternating sign. Later on, you'll take a list of numbers and have to write an equation. And if you notice alternating positives and negatives, try to involve this idea somehow of a negative 1 or a negative number raised to a power of like n, let's say. All right, and then lastly, we were supposed to find the 100th term, so that means that we're going to plug in a 100. So a sub 100 would equal negative 1 to the 100th power divided by 2 times 100 minus 1. Well, negative 1 to the 100th power, since it's even, that'll be a positive 1. And then we'll have 200 minus 1, which is 199 on the bottom. So that's our 100th term. So again, explicit means you can plug in whatever number of the term that you're trying to find. So if I want the 50th term, I plug in a 50. Okay, so just a little recap. Arithmetic is when you add the same thing each time. Geometric is when you multiply by the same thing each time. And those were nice because we had formulas. So an explicit formula for arithmetic was a sub n equals a sub 1 plus d times n minus 1. That was our explicit formula for arithmetic. For geometric, our explicit formula was a sub 1 times r to the n minus 1. So we had nice formulas. But not everything is going to be arithmetic or geometric. It might be neither. So you might have some other pattern. And this is where it gets a little trickier to come up with a formula. Okay, so that's kind of why section 8.1 sometimes seems harder, is because it might be some other random pattern that you have to find and then come up with an equation. So for example, we won't do both of these, but for example, this one right here. So if I saw that list of numbers, I'm going to hope that it's arithmetic or geometric because then I've got a formula I can use. So I'm just going to ask myself, am I multiplying or adding by the same thing each time? So like here, I'd have to add 4 to get to 7. 7 plus 4 is 11. 11 plus 4 is 15. 15 plus 4 is 19. Oh, this is arithmetic. That's awesome. Okay, so if I realize it's arithmetic, then I can write my explicit formula. My first term is a 3, and I'm adding 4 each time, times the quantity n minus 1. Boom, done, I got my formula. Don't have to think so hard. Let's look at this one. Are we adding the same thing each time? So you could find the common difference. So you could say, okay, well, 25 minus 17 is 8. How about 33 minus 25? That's 8. How about 41 minus 33? That's 8. Oh, look, this is arithmetic too. Bonus, so then my formula will be 17 plus 8 times n minus 1. Great. Okay, now if it happens to be geometric, if you're multiplying by the same thing each time, great, you've got a formula. But again, it's not always going to be arithmetic or geometric. So let's look at these examples here. Maybe we'll let's start with this one down here in the middle, kind of toward the bottom. Okay, so ask yourself, all right, am I adding the same thing each time? Well, 2 plus 4 is 6, but 6 plus 4 would be 10. So we're not adding the same thing each time because it looks like the amount that we're adding changes. So it's not arithmetic. So then we might say, well, is it geometric? Am I multiplying by the same thing each time? Well, 2 times 3 is 6. Is 6 times 3 12? Nope. 6 times 3 would be 18. So we're not multiplying by the same thing each time, so it's not geometric either. All right, so this is a neither problem, but you still might be asked to find an equation. So we have to look for a pattern. So kind of maybe pause this, see if you can find a pattern. Okay, now the main thing to writing an equation, an explicit equation, is that we need to be able to plug in the term in order to find our answer. So for example, you might want to write down the term numbers. Like this number 2 right here is the first term, 6 is the second term, 12 is the third term, 20 is the fourth term. So when I write my equation, I better get a 2 when I plug a 1 into my equation. I better get a 6 when I plug a 2 into my equation. and so on. So my equation has to involve something involving n, such that like when I plug a 3 in for n, I get a 12. So this is where it gets trickier. So what I would say to do, I'm going to erase this so I have some room to work. What I would say to do when you're writing an equation is always try to involve n. So ask yourself, how do I get a 2 from a 1? How do I get a 6 from a 2? How do I get a 12 from a 3? How do I get a 20 from a 4? And I'm going to try to color code this. So, all right, I'm looking at it, I'm thinking, well, I could get a 6 if I do a 2 times 3. And I could get a 12 if I take this number up here, 3, and I multiply it by a 4. And I could get a 20 if I take this number up here, which is a 4, and I multiply it by a 5. And I could go back to here, and I could get a 2 if I take this number up top and I multiply it by a 2. So what I'm trying to do is I'm trying to involve these n numbers so that I can write an equation. So again, 1 times 2 gave me 2. 2 times 3 gave me a 6. 3 times 4 gave me a 12. 4 times 5 gave me a 20. Now when I look at this, I'm noticing, oh, I always have, I want to color code it. I always have n times some number in pink. N times some pink number, n times some pink number, n times some pink number. Okay. Maybe it would help if I had these as pink. All right, well, how do I get that number in pink? Well, it seems like this pink number is always 1 bigger than the blue number. 1 bigger than 2, 1 bigger than 3, 1 bigger than 4. Well, if I know this front number is n, how do I get 1 bigger? Well, I would just do n plus 1. So if I know n is 2, I would do n plus 1 to get a 3. If n is 3, n plus 1 would be a 4, and so on. So it looks to me like the pattern is always I can take my value of n and multiply it by n plus 1, and that will give me any term. Now, if you're ever curious and you're like, I don't know if my formula is right, well, let's try it out. So think what would be the next number in this pattern? Like if you can establish the pattern, what would be the next number? Well, it looks like the next number would be 5 times 6, right? And 5 times 6 is 30. So let's try it out. Is my 5th term really 30? We'll plug a 5 in. 5 times 5 plus 1, that's 5 times 6, which is 30. And I could verify for any, like, let's say I want to verify my 2nd term. Is that really 2 times 2 plus 1? 2 times 3 is 6. Is my 2nd term really a 6? Yep, my 2nd term is a 6. My 5th term was a 30. Now, you should know that there's always more than one way to write an equation, so this is not the only correct equation. Some people look at this pattern. I'm going to write it over here. Some people look at this pattern and they see it in a little bit of a different way. Just make sure that you always relate it back to your term number. So your 1st term, 2nd, 3rd, 4th. So some people might be looking at these term numbers and they might be thinking, well, for example, if I square 4, if I do 4 squared, I'd get 16, and I'd have to add 4 to that to get to 20. And if I did 3 squared, I would get a 9, and I would have to add 3 to that to get a 12. Or here, if I did 2 squared, I would get a 4, and I would have to add 2 to that to get a 6. So it looks like I'm always taking my n and squaring it and then adding n to it. Well, that shouldn't be all that surprising because look what happens when you distribute the n through. You're going to get n squared plus n. So there's multiple ways of writing an equation is the bottom line. But this is where it gets tricky because you have to find a pattern, number one, and then number two, you have to relate it to the term number. So I always write the term numbers on top, and I always ask myself, how can I use these to get these terms in the sequence? Let's do another one, and this one will seem a little easier, I think. Up here with the fraction. Okay, so most people when they see the fractions, they kind of freak out because they're like, I don't know, what am I adding or multiplying by to get each fraction? But here's what I would say to do. Relate it to the term number. So this is the first term, second term, third term. Now, if I'm going to write an equation, a sub n equals, if I notice I always have fractions, I'm just going to automatically put a fraction bar. And then what I want to do is ask myself, how do I get these bottom numbers separately from how do I get these top numbers? And always relate them to n. So I'm looking and I'm noticing, oh, the bottom numbers, the denominators, are exactly whatever n is. So the denominator is just n. Then look at the tops, the numerators. How are we getting those numbers from these numbers, n? So like, what do I got to do to a 1 to get a 2? What do I have to do to a 2 to get a 3? What do I have to do to a 3 to get a 4? Well, it looks like these are just always 1 bigger, right? 3 plus 1 is 4, 2 plus 1 is 3, 1 plus 1 is 2. So it looks like I'm just taking those n values and I'm just adding 1, and that gives me my top value. That's it. That's your formula. And again, this is an explicit formula, so if I ever asked you to find a specific term, like let's say I want the 50th term, you just plug a 50 in and you're done. So if I want the 50th term, it would be 51 over 50. But if I want a formula, that's what's in the box. Just like down here, that would be our formula. All right, so let's look at this example here. So again, I write the term number, first term, second term, third term, fourth term, fifth term. I'm noticing that all of these are fractions, so I'm just going to put a fraction bar. This first 6, technically I can make it a fraction if I put it over 1. And I have to ask myself, and I would say look at the top separate from the bottom. So for example, let's say we look at the tops. How do I get a 6 from a 1? How do I get a 7 from a 2? How do I get an 8 from a 3? A 9 from a 4? A 10 from a 5? Well, it looks to me like these are always 5 bigger, right? 1 plus 5 is 6, 2 plus 5 is 7, 3 plus 5 is 8. So I'm just taking the n value and I'm adding 5 to it, and that helps me get my top number. Now let's look at the bottom numbers. How do I get a 1 from a 1? How do I get a 4 from a 2, a 9 from a 3, a 16 from a 4, and a 25 from a 5? Well, you might notice those are squares. 5 squared is 25, 4 squared is 16, 3 squared is 9, 2 squared is 4, 1 squared is 1. So I'm just taking these n values and I'm squaring them to get the bottom numbers. And that's my equation. So this is not arithmetic, it's not geometric. I don't have nice formulas to use, so I gotta kind of come up with my own formula. And again, that's what makes it tough. Okay? Now, all of those were explicit. Let me go back one more time. They were all explicit because I could plug in any value I want, and that's the term I would get. So if I want the 50th term, I plug in a 50. That's explicit. But now we're going to look at recursive. Recursive look a little bit different. In a recursive sequence, I'm going to give you a starting term or terms. So I'll give you some place to start. And then I'm going to give you a formula that's going to help you get the next term. Now, to get the next term, I have to plug in a previous term. So like let me write this out. If I want the 50th term, if I want the 50th term, I cannot just plug in a 50. I would have to plug in the 49th term. So I would have to know the 49th term, plug it in to get the 50th term. If I want the 100th term, I would have to know the 99th term and plug it in. So it's not as easy as just plugging in whatever number of the term I want. Let's try one out and so you can see how it works. So I'm telling you the first term is a 7. So in my list of numbers, the first term is a 7 for sure. If I want the second term, try to figure out where I want to write it. Let's say I want the second term. That would be denoted with an a sub 2. Okay, now what would I have to plug in for k in this equation in order to get an a sub 2? What would have to go in for k? Not a 2, because that would be 2 plus 1, which is 3. So I would have to plug in a 1 for k. Sorry, I'm just going to try to color code this as best as I can, which I know is a little tedious, but I think it might help. Okay, so that value of k has to be a 1. So that 1 plus 1 makes 2 for my second term. Now wherever I see a k, I'm going to plug in a 1. And I'm going to color code it. Okay, so I'm just writing my formula out. I'm plugging a 1 in wherever I see a k. I'm doing that right here. Okay, well, following the formula, then, I'm supposed to do 2 times a sub 1, which is the first term, which I know is a 7. So 2 times 7 minus 3. 14 minus 3, I'm going to get 11. So my second term is an 11. Okay, let's say I want to find my third term. The third term would be a sub 3. What do I need to plug in for k to make this subscript a 3? So I would have to plug in a 2 for k, and I'm going to plug a 2 in for k right here as well. Just color coding it, so I'm plugging a 2 in for k. All right, now this is calling for a sub 2, which I just found was 11. 2 times 11 minus 3, I'm going to get a 19. So my third term is a 19. Okay, fourth term. Fourth term is a sub 4. Okay, and so in order for this subscript to be a 4, what would I have to plug in for k in order to make this subscript a 4? K would have to be a 3. Ah, shoot. Sorry. I'm trying to color code it, but it's not going so smoothly. Okay, so this would have to be a 3 because 3 plus 1 would make 4 for my fourth term. Okay, plugging it into the formula. The value of k is a 3. Okay, 2 times a sub 3. Well, a sub 3 we just found was a 19. 2 times 19 minus 3, I'm going to get a 35. So that's my fourth term. Okay, so let's just recap. I was given my first term was a 7. I plugged that in and I got an 11. I plugged that in and I got a 19. I plugged that in and I got a 35. So in order to get 35, I had to plug in the previous term of 19. And in order to get 19, I had to plug in the previous term of 11. And in order to get 11, I had to plug in the previous term of 7. So that's what I'm saying up here. To get the next term, you have to plug in the previous term. So to get the fourth term, I had to plug in the third. To get the third term, I had to plug in the second, and so on. That's recursive. Okay? Let's try another one. This one is a little bit of a weird one because I'm giving you the first two terms. So I'm telling you the first term is a 1 and the second term is a 1. All right, so then I need to use this formula to find any other term. So let's say I want the third term. Okay, the third term would be a sub 3. But following this formula, it's a sub k plus 2. Okay, so what's going to have to go in for k? In order for the subscript to be a 3, k would have to be a 1. K right here would have to be a 1. So that 1 plus 2 makes a 3 for my third term. Following the formula, I'm supposed to do a sub k. Now remember, k is a 1. So that'll be a sub 1 plus a sub 1 plus 1. Because right now I'm plugging in a 1 for k. Okay, well, a sub 1 is my first term, which is a 1. And then this would be a sub 2, which is also a 1. I'm going to just write out every step and not skip over things. So let me just write this out nicer. A sub 1 plus, and then this would be an a sub 2. Okay, I know a sub 1 is a 1. I know a sub 2 is also a 1. Add them up, I get a 2. My third term is a 2. Let's try the fourth term. The fourth term would be a sub 4. What value of k would have to go in here to make this whole thing a 4? K would have to be a 2. So I'm going to put a 2 in for all of these k's. Okay, so I'm just going to write it out, and I'm going to plug a 2 in for all of the k's. I'm just following this formula, okay, right here. And I'm plugging in a 2 for k. Simplifying that down, I would have a squared plus, that's not a squared, I'm sorry, a sub 2 plus a sub 3. Sorry guys, I'm recording this at 11 p.m., which is really late for me. Okay, the second term is a 1. The third term we just found here is a 2. Add them up, we get a 3. So my fourth term is a 3. Now, if you start to notice a pattern, we can bypass some of this stuff, okay? Because sometimes this makes it look more complicated than it is. So see if you can notice this pattern, all right? The third term is made up of the first and second terms. The fourth term is made up of the second and third terms. So what do you think the fifth term is going to be made up of? It'll be made up of the third and the fourth terms. See that pattern? It goes 1, 2, 3, and then this goes 2, 3, 4. The third term was a 2. The fourth term was a 3. Add them up, I get a 5. Okay, here's another way to look at it. I'm taking, like in order to get a term, I'm taking the previous two terms and adding them up. So in order to get this 5, I added up the 2 and the 3. In order to get this 3, I added up the previous two terms, 1 and 2. In order to get this 2, I added up the previous two terms, 1 and 1. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, etc. This is a Fibonacci sequence. And all these pictures down here at the bottom are where you see these Fibonacci numbers in nature. If you look at a flower, the petals on the flower are going to probably have 3 petals or 5 petals or 8 or 13, etc. petals. Spirals follow these numbers. If you look at making squares in which you connect the corners with a curve, and as the squares get bigger and bigger and bigger, the area would be like an area of 2, an area of 3, an area of 5, an area of 8, etc. I mean, I would just say, like, Google Fibonacci and you're going to find lots of really cool things. Okay, so that's another example of a recursive sequence. But again, recursive just means you're going to be given a starting point, you're going to be given a formula, and in order to get any term, you have to plug in some terms before it. Okay, the last thing I want to talk about are called factorials. A factorial is going to be denoted with an exclamation mark. So when you see 3 factorial, it's not like, yay, 3, I'm so excited. It actually has a meaning in math. So when you see a factorial, that just means you're going to multiply all the numbers leading up to and including this. So all the numbers leading up to 3, 1, 2, and 3, I would multiply those together and I would get a 6. If I had 5 factorial, I would multiply all the numbers leading up to and including 5. So I would have 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1, which is still 120. So it's all about multiplying, and it's multiplying all the numbers leading up to and including that number. So here's the first 5 factorials. You might want to just kind of, be aware of these numbers. And because if you see those in a problem and you have to write an equation, it would be helpful to recognize this pattern as factorials. Just like it's helpful to realize, like, this pattern, for example. Okay, so hopefully you're looking at this and you're like, oh, those are all just squared. Yeah, so 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, etc. Recognizing those patterns of numbers is really helpful. All right, well, anyway, I could give you a problem like this and ask you to simplify it. Now, there's different ways to do it, but I just want to kind of show you a relatively fast way that you can do that you probably wouldn't need a calculator for very much. So if I was going to write out 8 factorial, that would be 1, 2, 3, 4, 5, 6, 7, 8 all multiplied together. So that's on the top of my fraction. In a different color, I'm going to write out 2 factorial, which would just be 1 times 2. And then in a third color, I'm going to write out 6 factorial. And these are being multiplied, so I can put a multiplication symbol. 6 factorial would be 1, 2, 3, 4, 5, 6, all multiplied together. Okay, now realize you are multiplying, so any common factors on top and bottom will cancel. So the 1, 2, 3, 4, 5, 6 on top and the 1, 2, 3, 4, 5, 6 on the bottom, those will cancel with each other. Okay, because we're multiplying, so common factors will cancel. Now on the top, I'm just left with a 7 times an 8. And on the bottom, I'm just left with a 1 times a 2. And I don't need a calculator for that. I know the top is 56. I know the bottom is 2. And when I divide those, I get 28. So I don't have to really deal with, because these would be huge numbers, I don't have to actually figure out what those huge numbers are. I'm just going to use my idea of canceling to simplify it. So let me give you another example. So like if I have 2 factorial, I'm going to write that as 1 times 2, and then I'll do a different color I'm multiplying 6 factorial, which would be 1, 2, 3, 4, 5, 6, all multiplied together. And then in the denominator, I will do a different color. 3 factorial would be 1 times 2 times 3. And then 5 factorial would be 1, 2, 3, 4, 5, all multiplied together. And then let's cancel the stuff that is common on the top and the bottom. So for example, I've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 on top and bottom. Those would cancel. And I also have a 1, 2, and a 1, 2 on top and bottom. That would cancel. So all that's left on the top is a 6, and all that's left on the bottom is a 3. And when I divide those, I get a 2. Boom, done. Didn't need a calculator. Super easy. Okay? All right, that's enough for today. We will spend some more time on section 8.1. There's more to it, but that's good enough for now. All right, hope you guys have a good day. Bye.